Okay, the problem we're going to try to address is how to do extended computation in a GTK function. So if somebody clicks a button and you go into the function that handles the button click, and you need to do something extensive, some extended computation, some extended activity, the GUI, the graphical part, is locked up while you're doing that. It's not unlocked until you return from that function. So you really need to process things relatively quickly and return. All right, so how do you do extended computation? Well, one way is you could use the system function and run a command in a bash shell that's running detached or in parallel. With, command that has an ampersand at the end of it that detaches the task and it's running in parallel. And your GUI can function, your button function can return back to the host GTK thread, and everything's fine. The problem is you can't really communicate with that shell very well. There's possibility of semaphores and complicated shared memory arrangements, or you can have it write out to disk and process it that way, but it's cumbersome. So the other possibility, a popen won't work, by the way, because a popen is attached by a pipe to your task, and your task is locked with that. You can't run it in a detached mode, really. So anyway, when you could fork the GUI. When you fork the GUI, you get a separate copy. You get a child copy of the GUI program. It's got the value of all of the variables at the instant of forking. But there's some things it can't do. It does not have the main thread of the GTK handler running. It doesn't have the timer threads. What this means is that if somebody clicks on a button, the child does not get that signal. If the child may have a copy of the timer function, but the thread that's running the timer function is not functional in the child. So the child is dead with regard to the visual on screen. Nothing the child can do can alter the visual. You can't go in there, for example, if you have the pointer to a label and modify the text. If you try to do it, you'll get a lot of very odd-looking error messages. It simply won't work because it's in a different thread. So how do you communicate back and forth between the child and the parent? Well, the way you do it is actually with shared memory, but it's a simpler form of shared memory. You set up in your main GUI as global variables a set of pointers that point to data areas that are in shared memory. Now, any modifications, when you fork to the child, of course, has the addresses of these shared memory areas, and the child can modify these shared memory areas. If the parent periodically looks at these shared memory areas and looks for changes, then you can communicate back and forth. So, for example, as I'm going to do here, if we have a child that is wants to do something, it takes a period of time, and periodically tell the main program what it's doing, so the main program can modify a label to show the current progress. What the child would do is it would use the address of a shared entry or shared piece of memory. It would alter that shared memory, and once a second or so, the timer in the main program will update, let us say, the label on the screen with the contents of that shared area. So it does work. Now, I've got it sounds complicated. It's really not. The basic bottom line is that if you fork the child process of the fork can't access the GUI and shouldn't try to. Only the original parent can access the GUI. Only the original parent will have the timer. Only the original parent will respond to buttons and other events on the screen. However, the child can modify shared data areas that the parent can look at, and the parent can then proceed accordingly. All right, what we've got here is I've added some more stuff to this growing collection of widgets and so forth. A button called Find Ping Time. It's a very simple button. It doesn't really do much of anything. Its name is, boy, I've got the name keeps getting screwed up here. I don't know why. Now it's got a slash in it. All right, ping time is the ID on the thing. The signals are on ping time clicked. That's the only thing. So when you click it, it goes to a function on ping time clicked. Very simple. We have a label. The label is called ping time display. there are no signals for it because it's just a label value will be inserted in here. So those are the two changes to the GUI, to the Glade code that I've made. Now, what's going to... now, the code here, I had to come up with something that took time to do, that everybody could do if you wanted to get a copy of this code. So I've contrived an example that takes time to do. It takes about 10 seconds to finish. Could take longer if you wanted to. But it's not really doing anything significant. It's just an example to prove the point. So all right. First of all, I'll go down to the end and show you what I add these things at the end, as you probably have gathered. There is on ping time clicked. Now, here's where the fork takes place. We're going to get to that in a minute. Here is a popen. Here is the dummy task that's going to take a long time to prove the point. Now, what I do is I run a popen, which creates a shell and runs this command in the shell. The command I'm running is a ping. And I'm telling ping to run 10 times. Ping runs once a second, so it'll be 10 seconds before this thing is completely finished. Every result of the ping will be written back through the pipe that the popen creates with my program. So I'm going to do the ping. The ping is going to do it. The ping is going to happen 10 times. Going to get 10 lines of results, and it's pinging the website of my university. And so it'll come back and give the usual result from a ping, which is, let's see here. Let's just see what it runs as. You can see what the actual code is. That was a Control-Shift-C, by the way. If you know, you can cut and paste stuff out of a terminal window, and Control-Shift-V, and this is what the ping looks like. First line is different. Otherwise, it comes back and it tells me where it's pinging, and basically the thing that's interesting is the last bit, the time, which runs about 43 milliseconds to get out there, and then it gives a summary. So that's what ping does. It takes 10 seconds. Each individual ping is about 1 second. It takes about 10 seconds to do all of them. Each individual ping will result in a line being written to the pipe that can be read by the program. So what have we got? We declare a file pointer F1. We run the popen function. We pass to it the command ping that you see. And we tell the popen that we want to read the result. There's two options. One, you can write to the shell, or you can read from the shell. I'm reading from the shell. So it'll be an input, as far as my program is concerned, an input operation. The file pointer is open for read. Okay, if it comes back null, something horrible has happened, and exit will take place. Exit is normally used to kill off the child. The first couple examples I'm going to do, the parent will be the child. There will be no child. This will be a parent program, and the exit will kill the parent. And you could pass a parameter saying, giving some information about the reason for termination. Anyway, so if the pointer comes back, it means something went wrong with the popen. All right, let's assume it works. It normally does. Then I come down to a loop, and the loop is basically the loop is simply going to read from that pipe. There's the fgets, and I'm fgetting into the character string name, which is 512 bytes long, from the file pointer of F1, or from the pipe pointed to by F1, with a maximum length of 512. Okay. If it comes back null, it means it's finished, it's done, no more outputs coming, the shell is quit. So I close F1 and I exit, and that's it. All right, going up here we have, of course, name was declared, and I have a pointer P1. This ping flag we'll get to later. This is part of shared memory. This is a way of for the parent program to talk to the child program, but let's leave that off for a moment. Let's just look at the regular code. str is a function which finds the second string in the first string. And as you remember, time equals is at the end of each line of valid ping information. There's some lines that don't have time equals in them, but most do. So what I do is I get a pointer to the first character of the figure time equals. So it'll be a pointer to t in the string name. All right. Or it'll be null if it can't find it. If it is null, I just continue and the loop cycles, because there are lines that don't contain time equals. All right, then I print it out. I'm simply printing out to the terminal, and you'll see it when I run it, and it'll be in the background terminal. Result is, and I should probably, let's change that to equal sign. I think it looks a little better. But anyway, %s, and what I'm printing is starting at the byte pointed to by P1, so it'll be starting at time equals, at the T of time equals in each of these strings. And I'll see the latter part, the last bit on the line. And then this is another part of shared memory. This is where we're copying it back to the main program. Get to that later. It works, but we'll get to the. So I just want to do it without the forking. So I'll go up here and I'll insert comments here. So no forking, okay? And the forking is out. This is just a regular program. It comes down, opens a pipe to a shell, and does the pings, reads them in, and processes as we showed. Okay, let's see how it works. First I'll have to compile it, and then I'll run it. And there you see the my GUI. Now you'll notice here the clock is ticking up. This is in the timer. The timer once every second looks at the clock and updates this label. And you notice it's clicking up. The time is advancing. Now when I click this thing here, it's going the find ping time. It's going to go down to that function, and it's going to start reading the pings. And it's going to wait for each of the reads to take place. And it's going to take about 10 seconds before they're all read. During that time, you'll notice the clock will halt because the GUI is dead. Nothing in the GUI is running. So here we go. All right, there's the pings, and you'll notice the clock here is not advancing. As a matter of fact, if I click the X up here, nothing happens. It will now die because it hit an exit. It hit an exit at the end of the program. Excuse me, at the end of that function. So when we finally got the null from the fgets, closed F1, and we hit an exit, that exited the program. Me clicking the X box up here didn't work because the GUI was dead. It was waiting. All right. So there's the reason why you have to do something other than just doing it in the button, unless you're willing to have your GUI sit there dead part of the time. Okay, let's do the forking. Okay, in forking, as you know, I'm sure, the fork function actually creates the fork. There will be there'll be a copy created, and it returns a value. It's a process ID. It's an integer. And the data type now is PID_T, which is basically an integer. But in some future date, it may be something else. But for the time being, we ran into this problem with the clock, with the time, which was returning an unsigned long. But unsigned longs, we run out of unsigned longs in about 2 or 3 years, so it has to be a longer data type now. So we're going to have our own Y2K problem. But anyway, the fork takes place. If the value coming back from the fork is 0, you are the child. If the value coming back from the fork is non-zero, you are the parent. And the value is the process ID of the child. So both copies will execute the if statement. One is executing it as the parent, the other is executing it as the child. If it's the parent who will see a non-zero value for I, the parent returns. We've finished processing the button. The GUI is alive and well. If it's the child, this will be a 0, and we drop down and start doing this. All right. Now let's look at some of the other things here. Well, no, let's just plain run it, and I'll do some of the. Okay, there we are again. There's the clock timing up. Now when I click it, you'll notice this label here will get updated. And you'll notice the clock will stay running. And when it finishes with the pings, it won't kill the GUI. Okay, there we go. You can see them going in the background. And you can see the times being updated here. They weren't being updated before. You see the clock is still updating. Everything's fine. And until we get to the end of them, now they're done. And no more updates. The clock is still running, however. Everything's working fine. If I clicked it again, it would start up again. There's no specific termination or clearing. I should have, when I did all 10 of them, I probably should have cleared this out, or who cares. Anyway, you see it's updating and everybody's completely happy and the GUI didn't die or anything. How did this happen? Well, we go back in here. Well, it happened because of this line right here, string copy ping total p1. It's copying into a ping total is obviously a pointer. It's a pointer to a character string. It's copying the bytes beginning at the t of time equals in name. P1 is pointing into name. It's copying them into ping total. Ping total is in shared memory. And the timer looks at ping total and updates the label that we were watching with the... so you see that time equals appearing in the label because it's being copied to ping total, and ping total is shared. That's also the case with ping flag. Ping flag, if the ping flag becomes 0, we quit. As long as ping flag is 1, nothing happens. Ping flag will become 0 if the main GUI quits. That will cause any currently ongoing activity in this loop to terminate, as we'll see. Okay, so you got the two shared memory areas are ping flag and ping total. Both are pointers. Ping total is a pointer to a character array. Ping flag is a pointer to an integer. Star ping flag is the dereference of ping flag. So ping flag is a pointer. Star ping flag is the integer itself. It's a dereferencing if you haven't played with it. So, all right, back to the top. What have we done? First of all, we got a new include here, mman.h. This is the memory management routines. Got to have it. Don't have them, won't work. Okay, add it. Here is, we've added ping time and ping time display. Those are the widgets associated with the button and with the label. They're the same things we've done before. And I'll just jump right down here. You see ping time is brought in with the GTK builder, and ping display is brought in with the GTK builder. That sets up the button, and it sets up the label so we can use them. All right, that's not all. Okay, up here, so in other words, these guys here, ping time, ping display, they're just what we've done before for buttons and for labels, no big deal. Okay, here's what's different. Here is a pointer. You see, we're declaring ping total to be a pointer of type character pointer. What it's going to point to, of course, is going to be the first byte of a character array. So ping total is a char pointer. Ping flag is an int pointer. They're both pointers. This is declaring them as pointers. Star means dereference in open code. In a declaration, it means I'm a pointer. And we've also declaring a function here, on destroy, which I didn't have before. All right, let's go down and see where the shared memory is. Here is the shared memory right after the builder stuff. And it notes again, you got to have sys/, oops, there's too many M's there. Fix that. It's mman.h. First of all, we get the address of 512 bytes of shared memory. The mmap function will return me a pointer to 512 bytes of memory that will be shared. Now, it'll return a null if you run out of memory, but I don't think running out of memory is really much of a danger. Yeah, technically you should check to make sure it's not null. In a large program you would, of course. The shared memory will be accessible to the child. The child will get, when the fork takes place, the child will get the value in ping total. The value in ping total is to this shared memory. The shared memory is visible, there's only one copy of it, but it's visible to anybody, any of your tasks, any of your processes that have this address. So the parent process has the address ping total, and the child process has the address ping total, and they can both access the single piece of shared memory. It's seen by both of them. It's common to both of them. It's only one copy. That's important. All the other stuff is, unless it's constants or so forth, is not shared. The dynamic memory is not shared in a fork situation. The rest of the function, you can look it up. It's 2 lines there, so it didn't extend forever. But what that does is gets me the address of the first byte of a 512 byte area. Okay, there's my character string. And what I do initially, I copy in what was initially in the label. You can see there, tote playtime empty, and that was on the screen when it popped up first. And it's a pointer to a string, so you can copy into it using strcopy. And the pointer, of course, is ping total. Now the other one here is ping flag. This gives me the address of a 32-byte field, which I will treat as an integer. Now 32 bytes is too long. Generally speaking, you allocate these things in, it's kind of like binary powers and so forth. Because, well, I think the minimum allocation unit or by default is 16 bytes. Anyway, 32 is too large. But that gives me the address now. Since I treat it as an integer, it is an integer. So the next thing I do is, that's the dereferencing asterisk. So treating ping flag as the address of an integer, it is the integer, and I put a 1 in it. Which means, if you remember from the function down below, keep going until it gets to 0. You're on. You can keep running. When ping flag is turned to 0, then it tells that function, if you're still running, stop and exit. Now, this is not ideal way of doing it. I get 2 shared memory items. What would be more ideal is to have one structure and have the 2 items, ping total and ping flag, and perhaps other things, in that structure. And then I would only do one allocation, which would be a pointer to an area of memory that I would map the structure into. And I'd use size of and so forth to find the length or the size of the structure. So generally speaking, if you're going to have multiple shared memory entities, you probably want to put the pointers to them into a single structure and only do one memory allocation. This is legal. There's nothing wrong with it, but it'd be more efficient if you did it with a structure. Anyway, that being the case, I'm not here to teach structures, so this works. Now the other thing was that on destroy. Let's see, where is the where is the on destroy? It's down here something. Well, I'm going to search for destroy. Well, there it is at the bottom. There's the function on destroy. I missed it up top. Yeah, there it is. It's up at the beginning. It was prior to all the builder stuff. In the other programs, you will have noticed that this line was there, but it was slightly different. This is how to handle the destroy signal for the main window. The destroy signal for the main window, of course, is when you click the X up here. That's destroy the window. So what are you going to do with that signal? Now, in the past, it had been set to GTK quit, GTK main quit, and that signals GTK we're done. GTK closes out the window. Everything's fine. You don't do a return. You have to tell GTK to quit. Otherwise, part of your program is going to be left there as a zombie. So GTK main quit is important. But if you've got other things to do before you quit, you don't tell it to. This is where it had said GTK quit right in here. I removed that and I said, okay, when you get a destroy signal, what I want you to do is go to the function on destroy, and it will handle what's necessary. And when we see down here at the end, there's on destroy. It only does one other thing. It sets ping flag equal to 0. Since it's in shared memory, and the shared memory exists as long as either the parent or the child exists. So ping flag becomes 0, and if it happens to be running, if it's not running, the function here is, or this child is not running, it doesn't have any effect. But if the child happens to be running, setting ping flag to 0 will cause it next time it loops through here to see a 0 and cause it to exit. So I won't get, after the main program has died, I won't still be getting pings on the screen or whatever else. And then it goes to GTK main quit, and that terminates the parent program. The child program will terminate if it's running very quickly thereafter when it sees the ping flag equal to 0. So I guess I think I've covered everything. The main points, make sure you put the include file, sys/MMAN. Notice the sys/ in front of it. That's typical of before. I've added 2 pointers. These are global, by the way, so they can be seen by everybody. And the function declaration was required. I changed the destroy. So instead of GTK main quit, it's on destroy. And these buttons are the same as before. Well, they're just typical buttons. And then there's, oh, how does it work with how does it get updated? I forgot that. Okay, how does it get updated? Well, again, down at the bottom of the program here, you notice it was copying into ping total from P1. P1 pointing to that time equals whatever. It copies that string into ping total. Ping total, of course, is pointer to the shared character array. That means the parent program can now see it. So we go up to, and where I did it was in timer. Let me find the timer function down here. So I use the word timer too many times. All right, there's the Boolean timer, if you remember. It's been sitting there. It runs. There's where it grabs the clock and updates the label showing the clock. This is where it was updating the progress bar from a different video. And here is the one I've added. It is copying whatever's in ping total to the label pointed to by ping time display. That's that label right underneath the button. So the contents of ping total will be copied into the label, which will be visible on the screen. Since we're in the timer, we're in the main routine, it can update stuff. Now, this means it's going to do it every time, even if the child program's not running. It's a very tiny operation. You could, of course, put some flag in here that would indicate whether or not the child is running and whether or not to do this or not. Somehow I think the overhead of checking on it and doing it or not doing it, it might be higher than actually just doing it. It's like putting a timer on a 2-watt light bulb. The timer uses 7 watts. Just leave the light LED. I've got LED lights that are 1.5 watts. They're about the equivalent of a 15-watt incandescent. There is no sense putting a 7-watt timer on a 1.5-watt bulb. So likewise here, I'm not sure if setting it up so it doesn't update each travel. One thing that might be possible, might be more interesting. Let's add something down here. Is let's see, when we run out of them here. This is where we ran out of lines. And so this is where there's nothing else in the fgets. We've seen all 10 of them. And I just copied that line. Okay, put something like that in it. So, all right, run it again. Watch it again. All right, you notice it said ping time, and then it quickly switched to tote playtime empty. That's the first tick on the timer. It changed the default back here. If you remember, the default title in the GUI is ping time. So the very first instant you're going to see ping time. All right, so let's click it, and you see it started in the background, and it's chugging along, and they're updating. That's the update from the since they both be about the same amount of time. You can increase the frequency of updates. There's the done. The timer is set to go off once every second. You can set timers up. You can have multiple timers, and you can set the timers to go much faster than that. There's a different function for setting the time, but it's there. I've forgotten what the exact name of it is. The most efficient is to go once every second. You can go more than once every second, 3, 4, 5, 10 times a second, and you set it to in milliseconds, I believe it is, as to how frequently you want them done. But since this was only coming at me once a second, there's no sense really even worry about updating it more than once a second. But there it is. It allows you to do anything you want in a child process that has no effect on the main program. The main program keeps running. Now, again, using a ping was a contrived example. Your actual example could have been to be processing, media files or who knows what you would want to do. But it's an activity that takes time to finish. That would be impractical to finish inside the button processing for an individual button, because that button's going to lock up the GUI until it's finished. All right, that's that.